Okay, so hello everyone and welcome to MakeLearn 360. So in this video, I will solve a question with you to illustrate this concept of connecting rod, which sometimes act like a compound pendulum. Okay. So yeah, let's solve it together. So we've got a connecting rod, and then the mass is given as what? 450 kg, and then it's suspended on the ninth edge at a point which is 0.9. So let's call that point our D, the distance from the center of gravity, 0.9. Initially set at swinging over a range of what? So theta is 35 degrees on each side. Okay. So when the oscillation becomes small, the period of double swing is termed as, so period is 2.75 seconds. Determine the moment of inertia of the rod about an axis. So centroidal axis, actually determine the moment of inertia about the centroidal axis or the centroid, and then calculate the force on the ninth edge at the extreme end. Okay, so calculate the force. Okay, so this question is going to be simple if you understand what we called the compound pendulum. Essentially, what the diagram here is actually a simple pendulum, but I was drawing it to show you how the swinging motion is. So you go here and then you come here, that kind of term. Okay, that's the swinging motion. However, a typical compound pendulum will behave like this. Okay, and then you see that there is the weight coming vertically downwards as mj, and then there is the center of gravity, and then the distance from the center of gravity to the pivot, we call it the D. Okay, so normally that's how it works. And then the angle that it is inclined, in terms of the vertical, that's what we call the theta. Okay, so yeah, so that's a little bit, it just basically like how this one is. Okay, but this is a simple pendulum and this is a compound, but then the analogy is the same actually. So for small angles, then it behaves like a simple pendulum. Don't be confused about this, right? But then let's solve it as a compound pendulum. So for a compound pendulum, the period of a compound pendulum is given by 2 pi the square root of I naught divided by mj multiplied by d. Okay, where I naught is what? Ij plus m d squared. So Ij is the moment of inertia, or the mass moment of inertia about the centroidal axis, and then you add it to mass times what? The distance from the pivot to the centroidal axis, okay, or the center of gravity. So essentially, if you divide the period by 2 pi and square it up, it will be equal to Ij plus md squared, all divided by mg multiplied by d. Okay, so if you make Ij the subject, essentially Ij will be, okay, so making Ij the subject, first of all I will say that Ij will be what? So Ij will be equal to, or let me take my time and do it. So Ij plus md squared will be equal to what? Mj d, and this is being multiplied by t out of 2 pi all squared. So yes, essentially you just multiply this by that, and then you so you are going to subtract. Okay, so you say that Ij will be what? Mj d t over 2 pi squared minus what? M d squared. So that is it. Essentially, we have everything. The mass was given as 450 kilogram. We know J is 9.81 meter per second squared. We know that D is the distance, which is 0.9 meters. What else? And then the question said the period for double swing is 2.75 seconds. Now, some students will divide this by 2. But when you say double swing, it was just trying to tell you that it does this and does that. So that is essentially one sort of, if you do this, it's kind of like one complete revolution, actually. So that is the period. Okay. So if you put everything inside, Ij will be what? So it's going to be 459.81, and then D, which is 0.9. Then I will put 2.75 here divided by 2 pi all squared minus 450 into 0.9 all squared. And this is the Ig, which is the mass moment of inertia about the centroidal axis. Okay, so it's going to be 459.81 multiplied by 0.9 multiplied by, so I have 2.75 divided by 2 pi, and then this will multiply, so the square of this minus 450 multiplied by 0.9 squared, right? So essentially the answer is 396.6. So 396.6 kilogram meter squared, and that's kind of the mass moment of inertia. Okay, so the first part of the question has been solved. Now we move to the next part of the question, which says that we should determine, so initially it is set swinging over a range of 35 on either side. So this is why I brought this. So here will be 35, and then here will be 35. So it's like it's doing this kind of motion. It goes here, comes here, goes here, comes here, kind of thing. So that's what we are actually talking about. So we have been able to determine the mass moment of inertia, but he says we should calculate the force. So to be able to calculate the force, we'll use what we call the energy method. Okay, so we use what we call the energy method. Now, what is the energy method? So the energy method is that whenever you have a question here, okay, whenever you have a question like this, and then there is this simple pendulum, or let's say compound pendulum, which is doing this, okay, at some point in time, the maximum energy is such that, you know, the total kinetic energy in the system, so the total kinetic energy in the system will be equal to, okay, so the total kinetic energy of the system will be equal to the total potential energy of the system. In other words, this is actually a simple harmonic motion, okay? So the energy is conserved, right? So actually, we are assuming that the energy, which is in the form of the kinetic energy, will be equal to the kind of potential energy. That's what we want to say, okay? So then what we have to say is that if the kinetic energy is equal to the potential energy, then we can actually write this one. So we can say that mgh is equal to half I omega squared. In fact, it is the other way around, but it's the same, okay? So where this I naught is actually Ij plus m d squared, okay? So essentially that is the idea, but then we are going to use an h that we will apply in this formula, okay? Right. So if we kind of look at this, this is what we are going to do. First of all, we will calculate h. So when we say h, you see, okay, let me first of all calculate mgh, the potential energy of the system. So when we say h, in this case, so please everyone watch this. This is the pendulum, okay? This is the pendulum. So if the pendulum is doing this, okay, it will be doing this, right? But then with respect to, let's say if this was the first point at point 1 that is started from, it will get to a certain point here, and this is actually the equilibrium point, or where we have the maximum velocity occurring. Okay, for a simple pendulum, the maximum velocity occurs at this point. Okay, so at that point, the height will be given by L into 1 minus cos theta. Okay, why are we getting this? Because the whole length here, if you want to get the actual length here, it is going to be L cos theta. Okay, so if the whole length is L, and then this portion, so let me put it here. So it's like something like this. Sorry. So it's like this. So let's say that this is theta, then this side will be what? L cos theta. Okay, so if I want to get the kind of the potential difference, in fact, this is the point I'm interested in. Okay, but the whole of this, don't forget that the whole of this is L. That is the entire length. If you have a rod here, and then it is here, when it comes to the, when this one exactly comes here, it will be, the full length. But over here, this is L cos theta, which means if I want from here to here, okay, that one will be what? It will be L minus L cos theta. And that is the same as L1 minus what? Cos theta. So what we are trying to say is that at the maximum height, it will be J D mj d 1 minus cos theta. That's all what we are trying to say. So 450 times 9.81 times d, which is 0.9, 1 minus cosine 35. Okay, and that is so that's 450 multiplied by 9.81 multiplied by 0.9 into 1 minus cosine 35. So yeah, we have 718.5. So 718.5 joule, and this is sort of the potential energy, right? So if we are interested in the kinetic energy, all what we have to do is to we have to actually calculate this omega, because that is what will help us to calculate the dynamic force. Okay, right? So so we can say that 718.5 is equal to half. So the I in this case is going to be ij plus what? md squared. So this ij is actually what we just calculated for. Okay, so maybe let me calculate I naught. So it is 396 points. So this one, 396.6 plus, so 396.6 plus the mass, which is 450, and then multiply by d, which is 0.9 squared. So that's kind of the I naught. So 396.6 plus 450 multiplied by 0.9 squared, and essentially that's going to give me 761 point. So 761.1 kilogram meter squared. So this is actually the total inertia. Okay, so 761.1 omega squared. Okay, so if we solve for omega, what are we getting? So we can say that 2 into 718.5 will be what? 761.1 omega squared. So that the speed at the maximum speed is what we are actually after. So it's going to be square root of what? 2 times 718.5 all divided by 761.1, and that's essentially so square root of 2 times 718.5 divided by 761.1, and yeah, so that is 1.37. So that is the kind of, so 1.374 radian per second. Okay, sorry. So this is the speed, but you see, the speed will help us to calculate the force. Okay, so we want to calculate the radial force, which is the centripetal force, but then don't forget that the actual force will come in two components: the tangential force and the so the tangential component and the normal component. Okay, so the actual formula is, so this force is mg cos theta, okay, plus m omega squared d, m omega squared d. So actually this one I can't prove it because it's beyond the scope of this video if I have to prove it, but that's the formula. So 450 into 9.81 cosine 35 plus 450 into 1.374 squared, and you multiply it by the d, okay, which is 0.9. Okay, so this force is that force which he said we should calculate. So he said that calculate the force at the extreme swing. Okay, so at the extreme swing, that's why we are using the maximum so the maximum speed. Okay, right. So f will be given by 450 9.81 cosine 35 plus 450 multiplied by 1.374 squared multiplied by 0.9. So yeah, we are getting 4378.2, or let's say 4380.7, sorry, so 4380.74 newtons, right? So the reason why we didn't use this d here as d1 minus cos theta is because at this point in time you are just interested at the force at the ninth edge. Okay, so you are interested in the force at the ninth edge, but this one we were calculating for the maximum velocity. That is why we use the maximum potential energy. Okay, all right, so essentially this question has been solved. It's a bit tricky, but that is it. Thank you.